We will now look at evaluating AI model performance. After selecting the appropriate architecture, training and validating the algorithm, its performance must be evaluated against a set of data that is previously unseen, the test set. This will ultimately determine the extent to which the algorithm has achieved its goals. There are many ways to evaluate the performance of an ML algorithm, which are heavily influenced by the type of algorithm, the research question, and the clinical application. Exhaustive lists of performance metrics and how to calculate them are readily available in the literature and on the web. Some of the most common performance metrics in the healthcare domain and their key implications are mentioned here. We'll now take the example of an image classification algorithm aiming to differentiate between COVID pneumonitis (CP) and idiopathic pulmonary fibrosis (IPF) from chest CT scans. So these are two different conditions: COVID pneumonitis and idiopathic fibrosis. The algorithm classification or prediction is mentioned here, and the ground truth is mentioned here. The classification or prediction made by the algorithm can be classified in relation to the ground truth or the real diagnosis in a binary fashion, resulting in a 2 by 2 grid known as a confusion matrix. So this is known as a confusion matrix. This is a 2 by 2 grid. This can be done any number of times separately for each class. In cases in which multiple diagnosis predictions are outputted by the algorithm. So in this case, there are two classes, COVID pneumonitis and idiopathic fibrosis. That is why we have a 2 by 2 grid. When there are more than two classes, this grid can be extended by the side and below. For any number of classes, the grid can be extended. So this is the confusion matrix for binary class, and for more than two classes also we can extend the confusion matrix. From the confusion matrix, we can define four groups. The four groups are true positive, false positive, false negative, and true negative. True positive means the algorithm correctly predicted a true case of CP, COVID pneumonitis. So ground truth, COVID pneumonitis, algorithm prediction, COVID pneumonitis. So this is correctly diagnosed by the algorithm. So this is true positive. False positive, FP. The algorithm predicted CP. The algorithm predicted CP, but it was actually IPF. So ground truth is IPF, actually IPF, but predicted CP by the algorithm. So this is false positive. Fn, false negative. The algorithm predicted IPF. The algorithm predicted IPF, but it was actually CP, COVID pneumonitis ground truth. So this is false negative. Then TN, or true negative. The algorithm correctly predicted a true case of IPF. So idiopathic fibrosis predicted by the algorithm, and the actual diagnosis was also idiopathic fibrosis. So this is a true negative group. Actually, we can classify the two classes into arbitrarily into true class and positive class and a negative class. So in this case, we have arbitrarily classified COVID pneumonitis as a positive class and idiopathic fibrosis as a negative class. So that is why this is true positive, 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 and this is negative, negative. So this is true negative. So whenever looking at the confusion matrix, always look at this diagonal. This will give the true values, the true positive and the true negative. So which are actually the correct classifications by the algorithm. So always look at the diagonal values, this diagonal. So if these values are high, then it means the algorithm is good in correctly classifying the ground truth. And these values are the false values, false negative and false positive. Now, these are the common performance metrics for evaluating ML algorithms in healthcare. From the groups that we discussed, like true positive, false positive, true negative, and false negative, we can derive multiple common performance metrics like accuracy, sensitivity or recall, specificity, positive predictive value or precision, F score, precision recall curve, receiver operating characteristic or ROC curve. We'll first look at accuracy. Accuracy means the overall number of correct predictions compared to the entire number of predictions made. Sensitivity or recall means the algorithm's ability to correctly predict all cases with the label of interest. Specificity means the algorithm's ability to correctly predict all cases without the label of interest. Positive predictive value or precision means how many people predicted to have the label of interest by the algorithm truly have the label. This metric focuses on how useful the algorithm is in clinical practice. F score. F score is the harmonized average of precision and recall. This metric captures the trade-off between other metrics, which is very relevant to the healthcare domain and widely used in the healthcare ML literature. Precision recall curve. As the name suggests, this is a plot of the positive predictive value PPV and sensitivity or recall over the range of possible values that the dependent variable or variables can take. The curves can be studied to determine the optimal value of the variable at which the precision and recall are maximized. In healthcare ML research, this is particularly useful for determining the threshold for a classification algorithm. Receiver operating characteristic curve or ROC curve. Similar to the precision recall curve, the ROC plots sensitivity or true positive rate and specificity or true negative rate at all values of the dependent variable. The area under the curve AUC can be easily calculated to determine the aggregate performance of the model across all possible classification thresholds. A high AUC is desirable for most algorithms. This metric is widely used in the ML healthcare literature, in particular when comparing algorithms' performance to that of human experts, as in human versus computer experiments. Carefully choosing the most appropriate performance metric is of great importance to ensuring that algorithm evaluation is well matched for the desired clinical application. For example, a population-wide fecal occult blood detection algorithm for bowel cancer screening may aim to maximize specificity over sensitivity to avoid inappropriate investigations and avoidable anxiety for false positive cases, while an algorithm to determine which lesion should be biopsied during colonoscopy may rest the balance in favor of sensitivity to avoid missing cases at this key diagnostic stage.